Hi, today we'll do our discussion on triple integrals in spherical coordinates. We start with this example. You're asked to evaluate the triple integral of 1 over x squared plus y squared plus c squared over the solid G lying above the cone z equal to square root of x squared plus y squared and between the spheres x squared plus y squared plus c squared equal to 1 and x squared plus y squared plus c squared equal to 4. We begin by finding your spherical equations for your boundary surfaces, starting with the cone. From the lecture, this cone is just equivalent to phi equal to pi over 4 in spherical coordinates. As for your spheres centered at the origin, these are just equivalent to rho equal to the radius. So for this first sphere, we have rho equal to 1, the radius, and for the other sphere, you have rho equal to 2, the radius. So with our bounds already found, we can now present a sketch of your solid G. So here's a hand-drawn sketch of our solid G. Notice around the solid G, you have portion of your cone. Above the solid G, you have your portion of your sphere of radius 2, and below, you have your portion of your sphere of radius 1. Now, for each line emanating from the origin, we actually have our entry point to be at the sphere of radius 1, which is again given by rho equal to 1, and our exit point to be at the sphere of radius 2, which is again given by rho equal to 2. As such, we have your boundaries for rho, which will be from 1 up until 2. Now, for your theta bounds, we take a look at the projection of your solid G onto the xy plane. And for this particular example, we actually notice that all arguments from 0 to 2 pi will be covered in your projection. As such, your theta will run from 0 to 2 pi. As for phi, we will look at those lines emanating from the origin and we'll look at their behavior from positive z-axis to negative z-axis. And notice here for this solid G, the only values of phi that will be covered will be from p equal to 0, which is again represented by positive z-axis, up until the edge of your solid, which is given by the cone. But again, the cone is given by phi equal to pi over 4. As such, your phi bounds will actually be from 0 up until pi over 4. So with our bounds now found, we write our triple integral in spherical coordinates and we proceed with our evaluation. So again, we have this triple integral is now the integral from 0 to pi over 4. Those are your phi bounds. Integral from 0 to 2 pi, those are your theta bounds. Integral from 1 to 2, those are your rho bounds. Now, we replace this integral in spherical coordinates. Notice that the denominator, x squared plus y squared plus c squared, is just rho squared in your denominator. So you'll have 1 over rho squared. And here, we don't just replace dv by d rho, d phi, or d rho d theta d phi. We replace it by rho squared sine phi d rho d theta d phi, as we have here. We achieve a cancellation of the rho squared, of course. You're left with sine phi for your integrand, and this integrand does not contain rho nor theta. So integration with respect to rho and with respect to theta is as simple as multiplication by the lengths of the intervals of integration. So for instance, integration with respect to rho gives us 2 minus 1, which is 1. Integration with respect to theta gives us 2 pi minus 0, which is 2 pi. So you'll have 2 pi sine phi. And of course, the antiderivative of sine phi is negative cosine phi. So you're now left with this line, 2 pi times negative cosine phi evaluated from 0 to pi over 4. The evaluation of cosine phi at pi over 4 is square root of 2 over 2. The evaluation of cosine phi at 0 is 1. So with the negative sign considered, we now have this for your final answer. You have 2 pi multiplied by 1 minus square root of 2 over 2. For this next example, our solid G lies in the first octant under the cone z equal to square root of x squared plus y squared and within the sphere x squared plus y squared plus the square of z minus 2 all equal to 4. We look at the spherical equations of your boundary surfaces. Again, z equal to square root of x squared plus y squared corresponds to phi equal to pi over 4. As for your sphere, what we do here on the left-hand side is to expand z minus 2 quantity squared to get c squared minus 4c plus 4 all equal to 4. We have a cancellation of the 4, which gives us this 4 terms. The first three terms are equal to rho squared, and z here in the fourth term is just rho cosine phi by your conversion formulas. So you'll have, for the next line, rho squared minus 4 rho cosine phi is 0. So this gives us, upon factoring, rho times rho minus 4 cosine phi, which implies that either rho is 0 or rho equal to 4 cosine phi. We'll take this second one as the equation for your sphere, since the rho equal to 0 is actually included here when phi is equal to pi over 2. You get cosine of pi over 2 is 0, which gives us rho equal to 0. It's also interesting to take a look at the intersection of your two boundary surfaces. In this example, what we do is we take the square rather of both sides of this equation. You get c squared equal to x squared plus y squared and plug it in here. You get c squared plus c squared or twice of c squared, and you'll have minus 4c equal to 0. Cancel out the 2, factor out the z, you'll get z times z minus 2 is 0, which gives us c equal to 0 or c equal to 2. As such, the intersection of the two boundary surfaces occurs at the planes c equal to 0 and c equal to 2. Here's a nice sketch of your solid G. Near us, you have a portion of your sphere. Behind, you have your portion of your cone. And you actually have portions of your xz and your yz plane as well as boundary surfaces. Uh, this is because of the fact that your solid G lies only in the first octant. Now, if you take a look at lines emanating from the origin, the entry point for your solid is actually at the origin itself, which corresponds to rho equal to 0. The exit point is at rho equal to 4 cosine phi, which is the spherical boundary surface. So you have your rho bounds to be from 0 to 4 cosine phi. Now, for your theta bounds, in comparison to the previous example where we have all arguments of theta covered, this time since your solid only lies in the first octant and in turn the projection on the xy plane only covers the first quadrant, in fact all values in the first quadrant, will have your theta bound from 0 to pi over 2 only. Now for your phi bounds, notice that for the initial values of phi, there is actually no portion of your solid G covered. The initial value of phi that will be covered will actually be the one corresponding to this cone, which is given again by phi equal to pi over 4. And to cover the entirety of your spherical boundary surface, we must run phi from pi over 4 up until pi over 2, which represents the xy plane. So you'll have here your phi bounds from pi over 4 to pi over 2. So we now write your triple integral in terms of spherical coordinates. So if you have your triple integral with 1 as an integrand such as this one, this just represents your volume of your solid G. So we now write it as integral from pi over 4 to pi over 2. Those are your phi bounds. Your theta bounds is from 0 to pi over 2. Your rho bounds is from 0 to 4 cosine phi. And of course, don't forget your rho squared sine phi d rho d theta d phi. We integrate first with respect to rho. You get rho cubed over 3 for evaluation from 0 to 4 cosine phi. Of course, evaluation at 0 is 0. Evaluation at 4 cosine phi gives us 64 thirds cosine cube phi sine phi. Now we integrate with respect to theta. There is no theta here, so all we need to do is multiply by the length of the interval of integration, which happens to be pi over 2, so you get 32 pi over 3 upon cancellation. Now, integration with respect to phi at this point, you can perform a substitution. Let's say u equal to cosine phi, then negative differential of u is just sine phi d phi, which gives us the following antiderivative, negative 32 pi over 3 cosine to the fourth phi over 4 to be evaluated from pi over 4 to pi over 2. Notice here that if you evaluate cosine phi at pi over 2, you get 0. If you evaluate cosine phi at pi over 4, you get square root of 2 over 2. If you raise that to 4, you get 1/4. So what I did for this next line is first combine this 32 pi with the 4, so you'll get 8 pi. So you get negative 8 pi over 3, and you multiply that with the evaluation of cosine 4 of p at pi over 4 and at pi over 2, which is this one. So you'll get negative 8 pi over 3 multiplied by negative 1/4. Simplify that, you get for your final answer 2 pi over 3. Here, you have your triple integral of z over g, where g lies above the plane, z equal to 2, and within the sphere, x squared plus y squared plus c squared equal to 16, which is just equivalent, as we all know, to rho equal to the radius 4. Now, for the plane z equal to 2, we take a look at the conversion formulas. You get rho cosine phi for z, so this is equal to 2, gives us our spherical equation for the plane, which is just rho equal to 2 secant phi. So we'll look at the sketch of your solid G. Here below, you have your portion of the plane z equal to 2, and above you have your portion of the sphere of radius 4 centered at the origin. So you have this one. Now, it's very interesting up until which point are we covering here for each lines emanating from the origin. So in order for us to see that, we take a look at the intersection of the two boundary surfaces by plugging in z equal to 2 here. So you'll get x squared plus y squared plus 2 squared, which is 4, equal to 16. This gives us the equation x squared plus y squared equal to 12. Now we find the value of p that corresponds to this curve of intersection essentially. So you know for a fact that tan phi is given by square root of x squared plus y squared over z. But in this particular intersection, you have your z equal to 2, so that's the whole denominator. Your x squared plus y squared equal to 12, so the square root of that is just 2 square root of 3. So 2 square root of 3 over 2 gives a square root of 3. So here you have tan phi equal to square root of 3. And this corresponds to the value of phi equal to pi over 3. For the bounds, other bounds, we actually take a look at again the line from the origin. Entry point will be through the plane z equal to 2, which is again given in terms of spherical coordinates rho equal to 2 secant phi. Exit point will be through the sphere of radius 4, which is given by rho equal to 4. So you'll have bounds running from 2 secant phi to 4. For theta bounds, all arguments from 0 to 2 pi will be covered. Here you go. For phi bounds, again, as I've mentioned, the lines from the positive z-axis going to this negative z-axis from the origin will actually stop um, intersecting your solid at the curve of intersection, which is given by phi equal to pi over 3, or at least corresponds to phi equal to pi over 3. So your phi bounds will start from the positive z-axis going towards this edge of your solid given by phi equal to pi over 3. So you have this as your phi bound 0 to pi over 3. So now we write out your triple integral in spherical coordinates. You have integral from 0 to pi over 3, phi bounds, theta bounds 0 to 2 pi, rho bounds 2 secant phi up until 4. Z here is, by your conversion formulas, just rho cosine phi. Don't forget your rho squared sine phi. We simplify, you get rho cubed cosine phi sine phi. Integration with respect to rho is just rho to the fourth over 4. So you get rho to the 4 over 4 for evaluation from 4, from 2 secant phi rather to 4. Evaluate first at 4, you get 4 to the power 4 divided by 4, that's 64. 64 cosine phi sine phi. And then evaluation at 2 secant phi gives us, 16 over 4, which is just 4, secant to the power 4 of phi, which will, with the cosine phi, gives us secant cube of phi, or cosine cube of phi in the denominator, if we simplify. So you get negative 4 sine phi over cosine cube of phi for integration with respect to theta and phi na lamang. So yung integration with respect to theta gives us just 2 pi. Integration with respect to phi, for the first one, you can take perhaps, yeah, you can take q to be sine phi. You get differential phi is cosine phi, so you get sine phi squared over 2. This will give 64 over 2, which is 32. Now, for the other one, you can take your substitution to be q equal to cosine phi. Your differential of u will be negative sine phi. That will be in turn equal to negative or positive 4 over u squared, which gives us the following antiderivative upon that substitution. You get negative 2 over 1 cosine squared phi. And this antiderivative will be evaluated from 0 to pi over 3. If you evaluate 32 sine squared phi at pi over 3, you actually get 3/4. Sine of pi over 3 is just square root of 3/2. Next, you evaluate cosine squared of phi, or cosine of phi rather, at pi over 3, you get 1/2. You square that, you get 1/4. You take the reciprocal, you get 4. So you get minus 2 times 4. And then finally, for the evaluations at 0, this is of course 0 at 0. Cosine of 0 is just 1, so you get minus 2 for your last part of this line. So simplifying things, you get 32 over 4 is 8 times 324 minus 8 is 18 plus 2 is 18. So you get 2 pi times 18, you get 36 pi over 36, you get 36 pi for your final answer. For this next example, you're given a triple integral in rectangular coordinates, and we will set up an equivalent triple integral in spherical coordinates. So we begin by taking a look at your bounds. For z, you get z equal to square root of 3x squared plus 3y squared, which is a cone. You have z equal to 3, which is a plane. So what we do here is we find the spherical equations for those bounds. You have z equal to 3, which is just rho equal to 3 secant phi from our previous technique. As for z equal to square root of 3x squared plus 3y squared, again, tan phi is just square root of x squared plus y squared over z, where z there will be replaced by this one, which is essentially square root of 3 multiplied by square root of x squared plus y squared. So the square root of x squared plus y squared will cancel out, and you're left with a square root of 3 in the denominator, which gives us tan of phi equal to 1 over square root of 3. And in turn, phi is just pi over 6. So we have an idea now how our solid would look like. You have below your cone as a bound, above you have your plane as above, as a bound rather. So now, which portion of that solid will actually be covered by this triple integral? And to answer that question, we take a look at the other limits of integration. So note here that your x runs from 0 to square root of 3, whereas your y runs from 0 to square root of 3 minus x squared. So from your double integrals, we know that this limits of integrations will actually just correspond to the projection, which is a quarter circle in the first quadrant centered at the origin of radius square root of 3. So these limits are solid for this triple integral to something in the first octant of this form. So you have here again, near us, you have your portion of your cone as your boundary. Above, you have your portion of your plane z equal to 3. And behind, you have portions of the xz and the yz plane. Okay? So we take a look at now your setup in triple integrals and spherical coordinates. We'll start with the phi bounds. So if you take a look at lines from the origin, starting with the positive z-axis, going towards the negative z-axis, it will actually stop intersecting the solid at the cone, which is given by phi equal to pi over 6 for this example. So you'll run your phi from the positive z-axis up until the cone, 0 to pi over 6 that is. So you get this bounds for phi. For theta, you get 0 to pi over 2 because your projection onto the xy plane is just on the first quadrant. All arguments in the first quadrant are covered. Now for your phi bounds, if you take a look at lines emanating from the origin, the entry point will be at the origin, so that's rho equal to 0, and the exit point will be through the plane z equal to 3, which is rho equal to 3 secant phi. So you get 0 to 3 secant phi. And then finally, for the integrand, x squared plus y squared plus c squared, or the square root of that, is just rho, as we all know. So again, we have rho here, and to complete the integral, you get rho squared sine phi d rho d theta d phi. We'll do the same process for this next example. You have another triple integral in rectangular coordinates. Your z bound here for the lower limit of integration is a cone, z equal to square root of x squared plus y squared, as we all know, is just equivalent to phi equal to pi over 4. On the other hand, you have z equal to square root of 18 minus x squared minus y squared, which is equivalent to x squared plus y squared plus c squared equal to 18, or at least this is part of this sphere of radius given by square root of 18 centered at the origin, which in spherical equations is just rho equal to 3 square root of 2. So this is an idea. You have a cone for a bound below, and for a bound above, you have a portion of your sphere. Now, to limit your cone, or your solid rather, for this particular triple integral, we take a look at the other bounds. So your y bounds here runs from 0 to 3, so, and your x bounds runs from negative square root of 9 minus y squared to 0. So this actually limits your what they call this, your projection onto the xy plane to a quarter circle, this time on the second quadrant of radius 3, centered still at the origin. So we now have this sketch. Notice here that I rotated your Cartesian space a bit. So you'll have your x here and your y. So just so the solid is near us. Still following the right hand rule, of course. You have still your cone below as a boundary surface. You have your um, portion of your sphere as a boundary surface above, and you have, of course, your planes to complete the bounds of your solid G. So we find your phi bounds first. Again, just like in the previous example, you have your phi bounds to be given by the cone, at least this the upper limit of integration. You have your phi running from 0 here up until the cone, which is given by phi over 4. So you'll have this. For theta, the projection is on the second quadrant, so your theta will actually run from pi over 2 to pi this time. For rho, entry point is still the origin, so you have 0. Exit point will be through rho equal to 3 square root of 2. So this is your rho. We don't have an integrand, so no conversion needed here. We just go and get rho squared sine phi d rho d theta d phi as your final answer. One more example under this type, you have z equal to square root of 3x squared plus 3y squared, and z equal to square root of 4 minus x squared minus y squared. Now, from our previous example, this cone z equal to square root of 3x squared plus 3y squared is just phi equal to pi over 6. Now, for z equal to square root of 4 minus x squared minus y squared, you have that to be equal to rho equal to 2. It's just a sphere centered at the origin of radius 2. The idea here is we have a cone below, and again another portion of your sphere, just like in the previous example. Now to take a look at the portion of your um, solid covered with the triple integral, we again look at the bounds. So your y here runs from -1 to 0. Your x here runs from negative square root of 1 minus y squared to 0. So this actually limits by your knowledge of double integrals. This is actually your quarter circle in the third quadrant this time of radius 1 centered at the origin. So a sketch of our solid will be something like this. Again, notice that here I rotated your Cartesian space in such a manner that the solid is nearer us. You have your x-axis here, your y-axis, and your z-axis here. Your phi bounds, much like the previous example, will run from 0 to the cone, which is given this time by pi over 6. So you'll have 0 to pi over 6. Theta bounds will depend rather on the projection onto the xy plane, which is on the third quadrant only this time. So your theta bounds will be from pi to 3 pi over 2. And for your raw bounds, you have entry point is at the origin, which corresponds to rho equal to 0. Exit point will be through rho equal to 2, which corresponds, or rather, which gives us 0 to 2 for your limit of integration. X here, you can easily convert using your conversion formulas. You get rho sine phi cosine theta. And of course, to complete this integral, you get rho squared sine phi d rho d theta d phi as your final answer. For this last example, we'll convert a triple integral in spherical coordinates into a triple integral in rectangular coordinates. Let's take a look at the bounds. You have rho equal to 0, the origin, up until rho equal to 2, which is a sphere centered at the origin of radius 2. As for your theta bounds runs from 0 to pi, which entails that your solid projects onto the first and second quadrant only. This limits your possible solid to something bounded by the XZ plane and the hemisphere centered at the origin of radius 2, where your y values must be greater than or equal to 0. Now, to finalize rather, your solid, we take a look at the phi bounds. Your phi runs from 0 to pi, and this is actually all values of phi possible. So this entails that the whole hemisphere is actually what we want here. So here's a sketch. Please excuse the sketch. Just use your powers of imagination to visualize that this is actually your hemisphere, and the bound below, or behind rather, is a portion of your XZ plane. The hemisphere or the sphere, rho equal to 2, corresponds to x squared plus y squared plus c squared equal to 4, which gives us c equal to plus or minus square root of 4 minus x squared minus y squared. The plus square root of 4 minus x squared minus y squared corresponds to the upper part of the hemisphere. The negative 1 corresponds to the lower part of the hemisphere. Now for z equal to 0, we actually get the projection of your solid onto the xy plane by this semicircle on the xy plane, which is given by, well, x squared plus y squared equal to 4. And to be precise, you'll have y equal to, or to be specific rather, you have y equal to square root of 4 minus x squared since you have y greater than or equal to 0. Now to finally convert your integrand, note here that you have to first factor out cross squared sine phi. So this will be the thing that will convert in terms of uh, rectangular coordinates. This will be part of the differentials essentially. So now look at this. We have your semicircle of radius 2 centered at the origin on the xy plane. And we know how to write out double integrals for those semicircles. You have your integral for x running from -2 up until 2. So this will be your x bounds. For y, again, you'll have from 0 up until this semicircle, which is given by square root of 1, or square root of 4 rather, minus x squared. So you'll have this for your limits of integration for y. And for your z will run from here to here, from the lower portion of the hemisphere to the upper portion of the hemisphere, which is given by negative and positive square root of 4 minus x squared minus y squared respectively. So you have this. And for your integrand, rho squared sine squared phi will actually be just given by x squared plus y squared. So you can verify that x squared plus y squared is just rho squared sine squared phi. So you have this one. And of course, you have the used ordering dz, dy, dx.